Hello all. Now let us deal with the prime and maximal ideals. So beforehand, before starting, let me recall what is meant by an ideal. So you have R as, just a minute. So your R is ring with unity and you are having subring N. How is N? When to say N is an ideal? So if you take A into N and you find that A into N is contained completely in N, or you have N into A, this is also completely contained in N, and this is true for all A's belonging to the ring. Then we say that N is an ideal. Did you follow the meaning of an ideal? So I would like to take you back to the definition of originally where we met the definition of ideal. Yes. So this is the definition of ideal. You can check it. An additive subgroup capital N of a ring capital R satisfying the properties AN subset of N and NB subset of N for all AB belonging to R is an ideal. So you can see here what we mean by this. You take left multiple of N. We are taking for all A's belonging to R. For every element belonging to R, we are saying so. I hope I'm properly audible, Gauri. Am I?
Oh, madam.
Okay. And if we are taking the right multiple, N into B, we are saying. So B is not actually any, it just is a representative. So I may say N into A, subset of N. Not need. It is not needed to take another symbol. You may continue with a single symbol also. So you can say AN subset of N or NA also subset of N. So whether you are taking left multiples or right multiples, both are contained in N, then we call A that N as an ideal of ring R. An ideal of ring R. I suppose you are following the definition. So let me take you back to this sheet. I have N. We are saying N is additive subgroup of R. So basically, let me recall what is ring. A ring is R along with plus and dot kind of operations on it. As far as R and plus are concerned, you know, R plus forms an abelian group. And there is multiplication defined on R. So what we are saying, N is additive subgroup means what? N is a subset of R and it satisfies all the properties of a group. So it's an additive group. Along with that, if you are having, yes, of course, this multiplicative structure is there. So if you take A, any A of this R, A times N means what? Every element of N we are multiplying left by A. So that set will be contained inside N. Every member of A into N is a member of N. At the same time, if I multiply on right side, still every member of NA must be contained in N. If this happens so, in that case, we say N is an ideal. So suppose you followed the definition of what is an ideal. Any doubt here? Anybody wants to say anything? Come on. How many of you understood the concept of an ideal? Okay, okay, it's good. I got 2 responses. All right. Now, I would like to go with our maximal ideal concept. The name itself indicates what is meant by maximal. At the same time, the name prime is also very important for us. The names are the labels, or actually they give you a certain hint. So let us now first proceed with the maximal ideal. Before going to maximal ideal, there are fixed ideals. You can see singleton zero. Is singleton zero an ideal? I'm just talking about singleton zero. Wait a minute, I have to just shift it. Okay. See, my ring is R. I didn't mention what kind of R I'm handling, but I said my set is singleton zero. This set let me denote by capital N for the time being because we are habitual of N. Now let me select any A from R. Actually, I should handle every A, but at this moment I'm saying I just handle single A from R. What is going to happen for as far as A into N is concerned? So I multiply by A to every member of N. There is single member. So A into 0 is, come on.
0.
Yes, it is there. Singleton 0. Set is over. Can I say it is a subset of N? I hope I can.
Yes.
At the same time, if I go like N times A, what do I get here?
0. Singleton 0.
Singleton 0. And again, it is a subset of N. So this A was arbitrary. So this is true for every A belonging to R. I'll be getting singleton 0 only, and it will be a subset of N. So you know very well singleton 0 is an ideal. Whatever ring it may be, singleton 0 is always an ideal. Did you follow the meaning? What I said? Got it? Because if I multiply by any element of the ring, A times N always becomes subset of N. At the same time, NA also becomes subset of N. So it is an ideal. I suppose you followed the concept of an ideal. Now what I'll do is, I'll go with another thing. I'll just take R as my N. So let me change the ink. Just a minute. This is too faint. Okay. So I would like to take R as N. And now let me select any member of R as I did earlier. And let me multiply by this A to R. What I'll get? Can anybody tell me what I'll get? What is R? What is R? Come on. What is R? How many of you know R? No one?
R is a ring?
Yes, R is a ring. So what will be A into R?
Ring?
See, what I mean is, if R is a ring, it will have two operations on it. What are the two operations?
Addition and multiplication?
Yes, addition and multiplication.
Multiplication.
Yes. Now here, which operation is used, Uddhav?
Ma'am, multiplication.
Yes, we are using multiplication. Very good. Now, what are the properties of multiplication in a ring? Yes, you know when to say multiplication satisfies these many things. And so this particular R becomes a ring. What are those?
Associative?
Yes, but before being associated.
Binary.
Yes, what is essential is binary. Binary means what? What is meant by binariness? Yes?
हा जे आन्सर असतं ते सेट मध्ये येतं आपल्या.
Yes, yes. whatever answer you are getting, it is back in the same set. So you see, A is out. I'm multiplying by A to every member of the ring. For the time being, let us denote it as, I'm saying, just a minute. I'm saying I collect all X over here such that, what is the property? Such that X belongs to R. Is it so? Such that X belongs to R. Now, if I multiply by A to the whole set, I will be getting elements of this kind, A into X. Can I say so? Such that X belongs to R. Okay. So what do I get in hand? What have I got here? Yes, what have I got here? See, A is a member of the ring. X is a member of the ring. So A into X is again a member of the ring. Do you agree? How many of you agree with me? Got me or not? If I multiply by A to every member of X, I will be getting all the members of the ring. So this set is going to be complete R, full of R. And that is why R, I can say, is a subset of R itself. R is a subset of R itself. Followed me? I suppose you got me. So whether I multiply by A to the left side or I multiply to the right side, multiplication is binary. And this being binary, RA will be R back. And it is, I can say it is a subset of itself. So what I mean by this, N equal to R is also an ideal. Whatever ring it may be, R itself is an ideal of itself. Singleton 0 is also an ideal of R. Whatever R it may be, whichever ring you handle, singleton 0 is always an ideal. And complete whole of R is again an ideal. So these are the two things you know very well. So this particular will be called as improper ideal. Both these are improper ideals. But out of that, singleton 0 is trivial one. So we will be labeling it as trivial ideal. This is an improper ideal. R itself is an improper ideal. And singleton 0 we will be labeling as trivial ideal. Followed me? Got the concept? Okay. So I would like to revise the same concept again. If I take singleton 0, तो singleton 0 को whether you multiply on left side by any element या फिर right side पे multiply करेंगे, answer will be 0 itself. So that becomes a subset of singleton 0, and that is why the set singleton 0 itself is an ideal, but it is a very trivial one, so we call it as trivial ideal. If I take whole of R, what is the problem? Whole of R will always satisfy the thing, so it is improper ideal. So what comes next is, what is a proper ideal then? What will be proper ideal? So damn sure R and singleton 0, they're obviously ideals. If there is any ideal different from this, that will be known as proper ideal. I suppose you followed me. So as we have seen in case of integers, There we used to say every number A divides itself. So A is always a divisor of itself. 1 divides A. Yes, 1 is obvious divisor. Okay, in every table you recite like 2 ones are 2, 3 ones are 3, A ones are A, likewise. So 1 is always a divisor of A. There is no, actually, what you can say, nobody will surprised by these two. It is damn sure that A and 1 will always be divisors of A. The same way, singleton 0 and R will always be ideals of R. So it happens, so they are improper ones. And as far as 0 is concerned, we call it as trivial one. Now, if you are having any other ideal than this, that ideal will be called as proper ideal. And in this book, they are saying it is proper non-trivial ideal. What they're saying? Proper non-trivial ideal. So which ideal is called as proper non-trivial? The ideal apart from or different than R itself and singleton 0 will be always called as proper non-trivial ideal. Saying proper is enough actually, but this book is using this terminology proper non-trivial. So I think you're following me. Now, next we go to, this is very important theorem you can say, you can watch here. If R is a ring with unity and N is an ideal of R containing a unit, they're not saying unity, what they say? Containing a unit, then N is nothing but R. N itself is R. I would like to revise, and this question has occurred in the previous question papers. What the statement says, if R is a ring with unity, unity means multiplicative identity, and unit means, I hope all of you are quite familiar with this.
Invertible element.
Yeah, it is an invertible element. And when I say invertible element, if I say, see here, if I say, let us go back again to our real number set. If I say 5 has inverse, at the same time, I can say 1 by 5 has inverse, multiplicative inverse, of course I'm talking. So does it not mean that 5 itself is inverse of 1 by 5?
Yes.
Obviously, if your element is invertible, that element itself is inverse of something else. This is the actual fact. Same fact we can use over here while proving this particular. But what we are going to prove, let us once again see too. R is a ring with unity. Unity is there. And N is an ideal of R. This statement is very important. N is an ideal of R. Means every multiple of N is a subset of N itself. And moreover, it contains a unit element, invertible element. If it is so, then N is not different than R, and itself is R. How will you go for this kind of proof? Of course, I'll be sharing this to you, but try to understand it. What is given? What is given to you? See, N, how is N? N contains unit element. So, I may say, suppose one element is there, suppose we denote it by U, U belongs to N. How is U? U is unit element. Means for U, we are having its inverse. So that U into U inverse will be, please, 1, of course. So this is its property. We are keeping this aside as a rough work for us. What we said, unit element is a member of N. I suppose you followed. And N is an ideal. So if N is an ideal, then A times N is always subset of N. This is our definition. A times N is a subset of n. This is the basic definition. At the same time, you can say n into a is also a subset of n. Followed? And what is this a? A is every member of R. So I have to use symbol. What is this? For all. So this statement holds for all A belonging to R. Sure? Now U is a unit element. Though it is present in N, basically U is a member of what? Come on. We have to restart then. R is a ring. Yes, R is a ring. R is a ring and N is subset of R. This is what we are saying. Now N contains few elements, so N is containing U. So what this statement tells you, U is a member of N, which is a subset of R, means U belongs to R. Do you agree?
Yes, ma'am.
So U is a member of R. And U is invertible, means U inverse will also be in R. I hope you agree. Agreed? Now, when we are saying this is an ideal, let us choose the value of A as U inverse. Can I? Actually, this holds for all. That is why I wrote this letter. I brought your attention to this particular. We are saying for all A's belonging to R. So particularly if I take A is equal to U inverse, then what will happen? I will multiply by U inverse to whole of N, and this will be a subset of N. I suppose you're getting. So this will contain what kind of elements? You can watch here. All elements are there, but one of the elements is what? One of the elements is U.
U.
And to this U, you are multiplying on the left by U inverse, as you are indicating here. All rest of the elements are there, no doubt. But I want to fetch your attention to this particular. And what is U inverse U?
1.
Yes, it is the unity. It is 1. So I can say this is equal to 1. What this means? 1 belongs to N. Do you agree? This is 1 and 1 belongs to N. I hope so. So this element is there. And what else you are saying at the same time? If I multiply by every A to N, it becomes a subset of N. Of course, for every A, if I multiply to this one, it will be certainly A. Means what? This has to be completely R. Did you follow the proof? What we did, let us once again visit. N was ideal. This was the definition of ideal. One more thing we wanted, that U should belong to N. U is invertible element. So it will have its inverse. Its inverse will be a member of R, of course. Now by this particular U inverse, if I multiply my N, somewhere I will be meeting U inverse U and I'll be getting 1. And this statement is true for all A's of R. By every member of R, if I multiply to this, and if it is a subset of N, obviously somewhere I'll be multiplying to 1 also. And I get complete set R over there. So this means we are having N is equal to R. I suppose you followed my proof. And this was one of the questions in previous question papers. You were asked to show this. Okay. Of course, I'm going to provide you this proof in written. Don't worry about that, but try to understand the facts. Shall I proceed?
Yes, ma'am.
Okay. Now, once again, I would like to read this proof in their terminology. See, n be an ideal of R. Suppose U belongs to n for some unit U in R. So we have taken unit element U from R as a member of n. Then the condition R into n is a subset of n for all R belonging to capital R implies if we take R equal to U inverse and U belongs to n. So 1 equal to U inverse U is in n. But you are saying that R into n is a subset of n for all R belonging to R. Will mean that R into 1 is equal to R is in n. And this is true for all R's belonging to n. Sorry, R. Will mean that the set n is nothing but the set R. Meaning thereby such an ideal which contains a unit element in a ring with unity, we always get n equal to R. I suppose you followed this. If not, we have to stress this fact. Shall I proceed? Come on. Should I repeat this?
Understood, ma'am.
Okay. Now I would like to go to this corollary. A field contains no proper non-trivial ideals. See to the statement. A field contains no proper non-trivial ideals. No proper non-trivial ideals means what? It will contain either singleton 0 or the field itself. And there will be no other ideal in it. So how would you prove it? Yes, anyone? What is field? When to say F is a field? F must be a ring itself. It should be commutative. Multiplication should be commutative. So commutative ring with unity. And every non-zero element is a unit element. Every non-zero element in F is a unit element. That is what we need here. So how will we prove it? Every non-zero element of a field is a unit. So what is going to happen? What is going to happen? If I collect elements, I mean as an ideal, if I collect the elements of F plus, then certainly it will have a unit element. And because it has a unit element, the ideal will be whole of R. In this case, the symbol we are using for R is F. So the field itself is its own ideal. So what are the ideals of this F? Either singleton 0 or all of F. So in case of an ideal, the only ideals of a field are singleton 0 and complete F. Followed the thing? Okay, okay. Simran, are you getting me?
Yes, ma'am.
Okay. Now let us move to the maximal ideal and then we'll proceed to the prime ideal. The name itself tells you it's a maximal. What do you mean by maximal? The largest of all. Means there is no bigger ideal than this particular. Then I'll call it as maximal. But of course, the ring R itself is an ideal. So if I have an hierarchy here, then it will be somewhat like this. Smallest ideal is singleton 0. The largest ideal is complete R. Then why to call it as maximal? So we discard this. We don't want this to. We want proper ideal. So a proper ideal. How it will be maximal then? So it will not have any ideal containing M. So here you can see maximal ideal of a ring R is an ideal M. It should be different from R such that there is no proper ideal N of R properly containing M. So there should not be any N which contains M. Means superset. So we don't want this. Okay, there should not be any proper ideal greater than this. So instead of saying greater, I would like to use the word superset. Followed the condition.
Means it should be less than R, no?
Yeah, every ideal must be smaller than M. Every ideal should be smaller than M. I would like to help you. Once again, let us show the diagram hierarchy of this. See, singleton 0 is always there, no doubt. R itself is always there, so I have drawn it at the topmost position. And suppose I'm having somewhere here I1, ideal I1, ideal I2, like this. Then I1 is contained in some J1, J2, likewise. So these are subsets, I can say. Okay, I'm using the symbol of subset. And here I'm having some M. And after M, I just have R. There is no other ideal between M and R. If this happens, then this M is the largest of all, and that is known as maximal ideal. We don't use word largest. We use the word maximal. Followed me? Okay.
Yes, ma'am.
Okay. These are actually sets. So whenever you talk about set, you'll be talking about which set is contained in which set. So we know the concept of subset and superset. So in set notation, M does not have any other superset than R. This is the meaning. Okay. So suppose you got this concept. All right. Now, I would like to take you next. So this is the definition of maximal ideal. And I suppose you followed me. Okay. Now you can see here, there is an example. If P is a prime, then you know very well that ZP is a field. Only for prime integers, ZP is a field. Do you remember this?
Yes, ma'am.
Yeah. Actually, ZP is not an, Zn is not an integral domain. Why for? Because there, if I take the example of Z6, you know, in Z6, 2 into 3 is equal to what?
0.
Yes. So 2 and 3 are known as divisors of 0 or 0 divisors. And whenever your set contains 0 divisors, it is not an integral domain. So Z6 is not an integral domain. But if you go for Z5, then 5 is prime. So
Yes.
Z5 does not contain 0 divisors, and that is why Z5 is an integral domain. I hope you remember it. You know that every non-zero element of Z5 is invertible. Why? Because 5 is prime. Z5 has every non-zero element as a unit element.